This is the last step of this proof. Step 4. From step 3 we have V is the direct sum of V1 and W, where W is invariant under T. Using the basis V1, V2 so on up to Vn of W1 and any basis of W as a basis of V, then by using the theorem 1, the matrix of T is of the form. That is, the theorem 1 says, that is, if V is the direct sum of V1, V2 so on up to Vk and each subspace Vi of V is of dimension Ni and this V1, V2 so on up to Vk are invariant under T, then a basis of V can be found so that matrix of T in this basis is of the form A1 0 so on up to 0, 0 A2 so on up to 0, 0 0 A3 so on up to 0, 0 0 so on up to Ak. So by using this theorem, here we have, that is, V1 is the direct sum of V1 and W and V1 and W both are invariant under T. Then by using the theorem 1, the matrix of T is of the form Mn1 0 0 A2, where A2 is the matrix of T2 is linear transformation induced by T on W. Since we know that T power N1 is equals to 0, now we get T2 N2 is equal to 0 for some N2 less than or equals to N. Repeat the same argument for T2 on W. We can decompose W as we did for V. So that is, ಇಲ್ಲಿ ನಾವೇನು ಮಾಡಿದ್ವಿ, V is decomposed into direct sum of V1 and W. So similarly here we have to decompose W. Okay, that is repeating the same argument for W and continuing this way, the basis of V in which the matrix of T is of the form. ಅಂದರೆ ಇದೇ ಪ್ರಾಸೆಸ್ನ ನಾವು ಇದೇ ಥರ ಡಬ್ಲ್ಯೂನ ಡಿಕಂಪೋಸ್ ಮಾಡಿದ್ದು ಮತ್ತು ಇದೇ ಥರ ಪ್ರಾಸೆಸ್ನ ರಿಪೀಟ್ ಮಾಡ್ದಂಗೆ. ಸೊ ವಿ ಗೆಟ್ matrix of T is of the form Mn1 0 so on up to 0, 0 Mn2 so on up to 0, 0 so on up to Mnr, where N1 plus N2 plus so on up to Nr is equal to dimension of V, and hence the proof is completed.